All right, I'm Drew. This is a presentation called How to Make Android's Bootable Recovery Work for You. So, nice to meet you. I'm a security consultant for NCC Group, formerly Monsanto Security. I focus primarily in mobile security and research. I've built Android firmware for 40 plus devices at this point. I'm part of the CyanogenMod project, port recovery and CM to new phones or phones that people hate. I also wrote and maintained the wiki for exploits and education on how to get started with Android. If you want to follow me on the internet, my cool guy handle is Ukanos. So what's this talk all about? I'm going to talk about why you need this, why you guys care. Talk a little bit about what bootable recovery is, what it does, what it doesn't do. We're going to learn how to map out a device that you've just either picked up off the shelf or that you have already and you're just curious to learn more about. Going to learn how to inspect some bootable firmware, and then we're going to talk about how you can flash some of these new images that you've created. So what is Android recovery? The stock recovery mode is a minimal bootable Linux environment that most, if not all, Android devices have. It provides tools to install new updates and repair a broken installation of Android. Used primarily to install signed OTA updates from your carrier or phone provider, and to reset the user data and cache partitions if you've made a mistake. Sometimes you have ADB access, which is the Android debug bridge, but for the most part, usually not, and it's a pretty useless tool outside of the two features I just mentioned. So custom recoveries, which is what we're going to be talking about today, provide root access and lots of useful binaries, and as you'll see, basically anything you want to have in there. It allows for easy backup of your essential firmware, so if you're experimenting, you start flashing things to your phone, it's always good to have a solid backup of this before you start messing around. And it provides a scriptable installation platform to install custom Android firmware, which makes this process a lot easier. So again, why is this significant? So custom recoveries provide a means to investigate, modify, and test new firmware. And in a lot of cases, it provides a vector to gain full control over a device. And as you can see here on the right, this is a custom recovery I built in the past, and very customizable, as you can see. So why do I need this? There's a lot of goals for this kind of software. Penetration testing, it's a great way to provide a way into a device that is not the running Android installation. So if you need to modify something and you want to do that without having to do it live, this is a good platform for that. It's a good way to gather data and do data forensics, and there'll be more on that towards the end of the presentation. This is also a great way to bypass security controls, because if you think about booting into a rooted Linux environment and the ability to mount any of Android's file systems read-write, there's a lot of potential for what you can do to remove a lock screen, for example, or anything that you might want to do like that. It's also very useful for Android testing and development. So if you're trying to port Android to a new phone, it's a good platform to test out your code and changes and roll back if what you've changed breaks things terribly. All right, so how do you make one? So the first thing we need to do is map out the device topology in full. You need the kernel source, and I'll get more into that later, but that's not always required, but you at least need the pre-built kernel from some existing boot image from the device. And then you need to build what's called an Android device configuration. And I'll show you how to do that as well. So bootable recovery. Excuse my shitty Jurassic Park joke here. I started to get into this because I realized, wow, this is just a little Linux environment. I know how to do this already. So I had a good stepping stone to get involved with this kind of thing. Every device is really a unique snowflake, as they say. You really cannot trust that even a device that's named the same thing but sold in different areas will have the same layout. Actually, you're going to find that that's really never all that true. OEMs have kind of gone out of their way lately to make this more standardized, which is good. But the canonical example I always give is like the Galaxy S2, there's probably 14 or 15 different versions of that phone. So just calling something by the sales name is never a good idea, and it's a terrible idea to assume that the partition layout's the same because this is how you brick a device permanently. So it's important to kind of treat these things as like everything is a new platform you've never seen. So the parts and structure of Android recovery. I'm going to talk about the main types. There's a lot of variants you see out there, but for the most part, probably 80% of like devices in the wild use the typical Android boot image, which consists of an Android boot header that we'll look at in a few, your kernel, and an initial RAM disk. There's also the init RAM-FS style, which Samsung pretty much was the lone wolf on this one, and they stopped doing this because it's crazy. But essentially what this is, the RAM disk is burned into the kernel itself instead of being part of an image, and essentially shares a single partition. So you have to flash an entire new kernel if you want a custom recovery, which, if you understand the point of recovery, is very stupid because you've broken your ability to boot the phone normally if you want to flash something custom and it doesn't work. So it sort of bypasses the whole idea of recovery, and they stopped doing this around the time the Galaxy S3 came out to the market. And then this is pretty much Sony has the same idea as what Samsung used to do, except it's actually an image instead of just the kernel itself, but it's a single partition. And this was essentially done originally just to save space, but now that we have very cheap storage in phones, Sony still persists to do this. So you'll see some variations like this out there in the wild. Here's a look at the most typical one, the initial RAM disk image. And kind of as I said there on the left, this is the basic structure of the image. And then 10 and 11, I've starred here. This is something new that people have started to do by attaching what's called like a DTB blob to this image at the end. This is the device tree, binary device tree blob, as they call it. And the idea behind this is that if Samsung releases a Galaxy Note 4, for example, and it's in a few different markets, the base image is going to be the same now, but the things that make the variants unique are going to be contained in something like a DTB. So you need to attach this to your image or you will get a terrible black screen and tears. So make sure if your image uses one of these that you snag these and reuse them. So the initial RAM disk, or the RAM-FS, loads a temporary root file system into memory, just like you would on a Linux box. Files needed in here specific for recovery mode operations. So the recovery binary itself lives in here. Usually you'll have BusyBox and a whole mess of symlinks back to BusyBox for like GNU tools that you might need. Init scripts and the init binary itself live in this image as well. Other images, other firmware, I've seen some insane things in some of these images, so you'll have fun kind of taking these apart, I think. And these can kind of be rebuilt or modified to include more tools and extend functionality. Typically, it's always better to compile one of these yourself, but in a lot of times, this is not realistic for a few reasons. A couple OEMs like Rockchip, or like, not OEMs, like SOC providers like MediaTek and stuff like that are really slow at providing kernel source, or have like stupid dependencies like kernel objects that have to be loaded. So it gets a little tricky to kind of build your own, and it's sometimes easier to just modify what's existing there. But it's kind of hacky, so we avoid that whenever possible. The other files you'll find in here, everything below and including Jelly Bean 422 uses a file called recovery.fstab. And if you've ever worked with like an etsy fstab file in Linux, it's essentially the exact same idea. It just maps the block devices and their file systems to mount points in the environment. This typically lives in the etsy or the res folder in the RAM disk. Modern devices, pretty much everything from Jelly Bean 4.3 and above, this nomenclature has changed slightly now to be fstab.platform. So for example, like .qualcomm or MSM8974 for that particular Snapdragon stock. Essentially the exact same idea. The mapping order is different though, so be careful with that because otherwise you'll get no file systems. So let's learn how to map out a device. The things you'll need to do this, the stock firmware, either the boot image or the recovery image, there's tons of places you can get this stuff online. There's sites dedicated to specific OEMs like Samsung, HTC, Motorola, stuff like that, where you can just get the base image for your device out there. However, a lot of times that's not always possible, so we need to pull it off the device, which is going to require root to use DD or something like that. And we'll see how that's possible on closed environments shortly. The use is basically like troubleshooting and recon. Like this is a great way to learn how your device works by pulling the stock firmware and just looking at the setup of it. And it gives you a lot of clues into how the device is built and the topology of it. I mentioned kernel source a little earlier. This is essential if you have like an init ramfs style because you have to rebuild the kernel in order to modify it. It's also really useful for making things smaller. So older devices really, there was not a big eye towards the bootable recovery environment on older devices, and space was limited. So you're going to run into a situation where to make anything useful, a lot of times, like you're going to have to trim down space in order to make it fit in the partition. So this is not really a problem with modern devices in the last few years because you'll see like 20 meg now associated to it. But I've gotten things to fit on like 3.5 meg before. So having the kernel source is great to chop out a bunch of crap you don't need in order to make all the stuff you do want fit properly in the image. And of course, you can modify the kernel to do anything you'd like in this case if you have the source. So that's useful for some purposes. We're going to look at the system build.prop file. So it lives in the normal Android system environment. It contains lots of parameters for setting various options within the operating system. For the purposes of this talk, we specifically want the board code name. And I mentioned before, like the sales name of device is a terrible way to define it because it doesn't really it doesn't really like specifically assign it to a particular thing, but the code name, the board code name will. So we can't really call this a Galaxy S2 anymore. We have to go by like what the actual code name is because that will be the specific partition layout and variant that we need. So this can be obtained from the system file, the system build.prop file. These two files, the proc eMMC or proc MTD, depending on the storage type you have, these don't always exist, but they're really nice if they do because this is a direct mapping of what the partition is and what's supposed to live on there. So that can save you a lot of guesswork and time. And then we'll look at the proc partitions file, specifically to get a list of all the partitions on the device, but also the sizes of them, which is going to be very important for building your own image here. And then this is more rare today to even find a config.gz. But this is useful for pulling the exact def config that was used to compile the kernel for this image. If you can't find this, you can usually find the kernel source out there depending on the OEM, but you'll run into things like HTC just strips out all the comments before they post the kernel source, so it's like a total pain in the ass to work with. So it's a little easier to kind of source these things differently sometimes. All right, so where do you find all this stuff? Let's look at how we're going to take apart some firmware here. So here's this is an image from the Droid DNA, I believe. And you can see I've bolded the interesting parts here. This is the Android boot header I mentioned earlier. This defines that this is an Android boot image. And then further down, the other bolded part, this is the kernel command line. This is passed in at boot time to the kernel that sets various options. Here we've got a serial interface that's set up, and a user debug profile is set with a specific integer here. So a lot of times, this is very important to put in your image because if you don't, it's not going to boot, or it's going to boot in a weird state, or just not provide what you need. So this is something else that's important to note on the source image you have, and then you should replicate this in your build as well. So there's various tools for this kind of thing that exist. Unpack boot image is pretty brittle and it's older at this point, and it only works on initial RAM disk images. So luckily that's the majority of things you'll find, but this thing will fall on its face pretty fast if you run into any issues. So you'll get seg faults, stuff like that. So the first command here is just basic usage of this. The input file is your firmware, the output file is whatever you want. And then you zcat the RAM disk that is extracted from it, pipe it to CPIO, and this will explode out the RAM disk and give you all the files of this boot image. And that's the stuff that we care about and that we're interested in. The more modern tool is MakeBoot. This one is very well maintained and supports lots of image types. And this is also much easier to use. So the second below there is the sample usage for MakeBoot. And all of these will be provided as like references at the end, so you can go find these tools online. Additionally, the unpack init ramfs is specifically for the Samsung case I mentioned earlier, where you just have a Z image and you need to pull files out of that. This is a little shell script just to do that for you. And failing that, good old binwalk can help you here as well in conjunction with DD. So if you just binwalk an image and you see where the RAM disk is, you can extract just that from the file using something like binwalk. You'll probably have to use a combination of some tools depending on the device in question here. So here's a sample output of MakeBoot. This is on the Galaxy Note 3. So I've bolded some interesting things here that you might want to pay attention to if you're building some of these things. So the kernel page size is very important. This has to be set right or you'll not get to space. You won't have any boot at all. More importantly, I think, though, the RAM disk offset is very important because now that partitions are larger and you're building custom images, it's not going to be able to find the RAM disk properly at boot time unless you set this, and you're just going to have a terrible failure for boot there. So this needs to be set properly to offset exactly where your RAM disk is. And then I sort of mentioned the DTB image earlier, as well as the kernel command line. These must be accounted for when you're building your own images. So our goal is to get the RAM disk and a working pre-built kernel. You know that the pre-built is going to boot the phone, so it's a good place to start there because they gave you this file already and you know that it boots. So it's better to start with a pre-built and then move into a custom kernel if you'd like. The RAM disk itself contains init scripts, custom scripts, and binaries that we need and we want in order to make this thing function properly. And this is also a great place to find bugs and a great way to find exploitation vectors for a device. And we'll see a little bit more about that coming up here. So why are these init scripts so important? As I mentioned, this is like an amazing source of bugs. People make terrible, sloppy mistakes in these files, especially on older devices. You know, some of these hilarious like 90s Unix bugs are back, like symlink attacks, way overly permissive files, exposed debug functionality, all sorts of stuff like that. And it also contains the services and the parameters for init for certain things that need to run properly. So sometimes you kind of have to account for these things. Everything is a hack in these, so like sometimes you just have to do what they're doing in order to make things work properly. So we're going to look at a couple examples here of like some failures in init scripts and how these things can help you root a device or find other exploitation vectors. So these are reprinted, of course, with kind permission from my friend John Sawyer, JCase, in the Android world. And these particular ones have been patched already, so I'm comfortable sharing these with you. But so here we can see basically a directory is created with far too permissive permissions, as well as a file mid.txt within that directory is 777, so this is world readable, writable, executable. So what can we do with something like this? So we push our root exploit to the device because data local writes is 777, so we have access to write to the data file system, which we should not have as a normal user. And now we're going to back up mid.txt, which already exists, because again, we have control of this file because it's 777. And then we're going to symlink a handy little tool called uEventHelper in the kernel to this file mid.txt. So further down, now that we've symlinked this, we're going to echo our root exploit to this file. And basically what happens is that U-event helper, when it executes, happens in the context of root in the kernel. And so now we've executed our exploit, and now we have root on the device. So, one example of two permissive permissions kind of biting us in the ass here. We'll look at another one that's also been patched, this time courtesy of HTC. We have a recovery directory, again, created 777 in the data directory. We also have a log file that we control because it's 666. We have world read and write on this file. So in this example, again, we can go to this directory as a normal shell user. We can delete the existing log file that exists. Now we're going to do a different style of attack. We're going to link data local.prop. And so earlier when I mentioned system build.prop, this is like parameters that Android understands that you can pass to it that set various options. There's an ability to sort of override or supplement the system version with one in data. So this is usually like a local.prop, so things can be set in this file here. So in this particular case, we're going to reboot to recovery to do this attack. We see our file here. We're going to echo the string ro.kernel.qemu equals 1 to this file. And basically what this tells ADB is that we're running in an emulator, and that ADB should, of course, just reboot as root, because we need that kind of control in the emulator. So we can cause an ADB reboot. It sees that it's in emulator mode now, supposedly, and now we have a temporary root shell in recovery, so that you can do a more permanent and persistent root via a method like this. So these are things that OEMs have figured out, like maybe we shouldn't do these things anymore. So you don't see a lot of these, but this stuff is still alive and well out there, and you can find it. And they've done things like improve init. They've done things like improve the ability for it to follow symlink. So they've added some protections to this, but these are wildly inconsistent, and you can still find stuff like this all the time. So what else in the RAM disk is interesting here? So watchdog daemons, this is something that sort of needs to bark at the kernel at certain intervals, so like 30 seconds, I've seen up to like 10 minutes before, where if this does not happen, it just pulls the carpet out from under you and the kernel just reboots the device. So if you're doing something important and this happens to you, it's not going to be good. So if you see something like this in your stock image that you're taking apart, you have to account for this in your image, or it's going to be terrible for you. There's also some necessary kernel objects sometime. I sort of alluded to that with like the Rockchip example, but Rockchip has done some insane things like try and wedge ext4 on top of like an MTD flash device, which just doesn't work. So they have to write their own flash translation layer. And therefore they have these proprietary kernel objects that have to be loaded at boot, or you just don't see any storage whatsoever. So things like that, you have to fudge version magic if you're building your own kernel. It's a little easier to just use what they've given you in that case and just hack it up. Sometimes you'll run into some standalone binaries in the RAM disk that are useful for operation or even required. And then you'll see some special commands, some debug functionality like that exposed in the RAM disk. So it's a good place to learn about potential ways into a device. So what if I can't figure these things out? This happens. Sometimes you just have a really tough device to look at. If you're lacking the firmware, you can kind of just do this by hand with a dumb shell user with ADB shell. The output of mount will help you at least identify a few key partitions. And then you can look at the sizes in proc partitions and sort of make educated guesses on where things are. So if you have a partition that's 2 gig, this is not going to be a boot firmware. So we can safely ignore this one. So you're looking for stuff in the range of 5 to 20 megabytes. And you can sort of pull images and just look at them and see, okay, yeah, this is what I need, or no, this is crap, or whatever. We'll talk about building the recovery here. So the Android build system is based on a meal ordering concept. Similar to if you like drive up to McDonald's and you have the 1 through 10 combo options, as they call it. So every device is a unique combo meal, as we say, and sometimes these combos can inherit from each other. So if you have, let's say, a device that has lots of variants, there'll probably be a common combo that these all inherit and make files from. And then the variant will have very small specific changes that happen. So sometimes you need to account for this. And the whole point of this is that we're building a new combo. We're going to put your favorite sandwich on the menu now. So how do we do this? You need something like CyanogenMod source. You can use the Android open source project source. Like any Android source you can find will do the job here. This will all come with bootable recovery. You're going to need something like Linux or OS X. You could do this in Windows via Cygwin if you really hate yourself, but I don't recommend that. And sort of all the info we've been talking about, all the stuff we've gathered earlier, you're going to need to build here. So there's a handy file that comes in the Android source called make_vendor. And make_vendor takes 3 parameters, and it builds you a basic combo. So here we see the example usage. The first parameter is the OEM, so this could be Samsung, Motorola, HTC, Sony, whatever. The second is the code name we found, the board name, the specific identification for this device. And the last is any bootable firmware. This could be a boot image, it could be the recovery, doesn't matter. make_vendor will take this, explode it out, and build you the combo and set up sort of all the mount points that you're going to need and all of the specific parameters. Unfortunately, make_vendor is terrible, and it's going to be incomplete and wrong. So it's going to help you get right off the ground and get you a skeleton config, but you're going to need to edit basically everything that it produces, or you're not going to get a good compile. So for the purposes of this specific talk, we're only going to reference these 3 important make files. There's lots of other things that happen here, but again, limited time here. So the board config, the fstab file, and the device codename make file. So here's an example again of the Droid DNA. I've marked the files that make_vendor creates with an X here so that you can see kind of what's generated. But there's plenty more files in a device config. And again, for the scope of this, we're only going to focus on recovery, but this is going to grow exponentially the more you start hacking on a device. The board config contains all the essential information about your device's board, the SoC, CPU, various hardware, Wi-Fi, Bluetooth, stuff like that, and some weird device-specific oddities sometimes. This is going to require the most modification, and it's going to continually evolve the further in the process you get. So this is something you're going to have to continually edit and hack up. And we're only going to talk about the very basic necessities to get recovery off the ground here today. So here's 2 parameters to pay attention to. I sort of alluded to this earlier with the RAM disk offset. The first command is deprecated after Jelly Bean 4.1 and in favor of the new one, which is make boot args. But this is going to be used to force a RAM disk offset for you. So this is important now when devices ship with larger partitions. You're going to have to account for these things. And this is how you set that offset in that file. The device codename itself contains instructions on where applications are and where they should be put in your output. So if you have to account for a watchdog daemon or some other file that's included in the stock recovery, this will map where it is in your combo config and where it needs to live in the compiled image when you're done. And again, this is essential for replicating OEM hacks and specific oddities that you see out there. So now we're going to build it. So we use lunch because we have this whole hilarious combo idea. You're going to load some environment variables here. You're going to call lunch on your combo config, and then you can call make. There's lots of make targets. I would say just read the make files if you're interested in other things. For the purposes of this is the initial RAM disk, very typical Android boot image. So recovery image is the name of that target. That's what we want to build here. Test it. Before you even attempt to flash this to your device, take it apart with the same tools we just talked about with the stock one, and you'll save yourself a lot of hassle because you can notice problems immediately and then not waste a flash cycle and or brick your device in a lot of cases. So make sure that the kernel's there, make sure the offsets are proper, make sure that the DTB exists in the right place, stuff like that. And again, compare to the stock image, compare to what we just took apart, and make sure that these things line up properly. And then, of course, make sure it fits, because if you build something larger than the partition, you're going to have a bad time if you flash that. So some common issues. This is what it feels like to build one of these sometimes. You just mash the keyboard until it works. But you're not going to get a boot on the first try. It's very rare. More realistically, you're going to get some failures here. So again, common things, RAM disk offset or the kernel page size is wrong. You have a wrong init Binary, you have the wrong init scripts. You're not emulating some weird OEM hack properly, or like the DTB file is wrong or missing, things like that. These are common things. If these don't work, it gets a little bit more hacky, but again, sort of outside of the scope of this talk. So now we want to flash it. Once we're ready to boot it, we've verified everything looks legit. There's some common methods to do this, and sort of this is where this talk sort of gets more interesting in the sense that, some of you are probably saying, well, yeah, these things are locked. Maybe we can find a root exploit, but that doesn't always help us in some cases, flashing these images. So here's some things that, are provided by some OEMs that just sort of fall short in the security context. So of course, DD is a good way to flash this if you have root and there's no additional write protections on the device. For hints on that, kind of refer back to the init script portion of this talk. The flash image binary is pretty much for MTD flash devices. This is largely deprecated now. No one really uses this anymore except on low-end gear. We're going to talk about Odin and Heimdall, and specifically download mode, which is provided by Samsung devices. And hopefully that scares some of you a little bit. We're going to talk a little bit about fastboot. Some of you may already be aware of that. This is various implementations of this across different devices. And then we have a newcomer to the game from LG, Laugh, which is a good title for it because it's terrible. So we'll look at these things coming up here. So download mode from Samsung is a special boot mode that you can put your device in that is completely permissive and sucks down any raw image that you flash to the device without very much verification at all. There are a handful of models sold only in the US on Verizon and AT&T, which actually enforce the signature checks on the boot image. So the big flagships on those two carriers at this point are kind of dead in the water. Everything else, including all international models, ships with this mode and just sucks in whatever you provide it. So when they say, like, if you lose physical access to a device, consider it compromised, like, here's a very specific and exact reason why this is possible. So I sort of mentioned download mode is a specific a specific Samsung bootloader interface that's shipped on all their devices. It requires very specific naming of the images in order to flash properly. Internally, Samsung uses a tool called Odin to interact with this device and flash firmware. This is a Windows-only closed source application that's leaked from like internal Samsung, and it is terrible. And so here's a picture of this software. Sometimes you need this. Some devices just will not talk to anything but Odin. But I would avoid this software if at all possible. And there's an alternative, luckily, to this called Heimdall that we'll talk about here in a second. But download mode, and specifically Odin, requires a U-star formatted tar archive containing the exact name of the image that you want to flash. And sort of hilariously, this is something you can't really natively create in Windows that requires a Windows-only application to flash. So it's kind of a weird scenario. But if you want to make your own, here's how to do that. Create your U-star formatted tar archive. Odin sometimes gets cranky if there's no checksum. It's always better to just do this because it'll work either way. But a lot of times Odin won't like pass a file if it doesn't check out its checksum. So here's how to attach one. And you sort of rename this file tar.md5, and then you can flash it in Odin. Luckily, a guy in Australia called Ben Bootable reversed how Odin works and created a program called Heimdall. And this is a cross-platform application that you can compile on any computer you'd like. It's capable of writing raw images and does not care at all about what they're called. So this is much more extendable and flexible, and it's easier to use than Odin. And we like this. But this does not work on all devices. Sometimes there's some weird boot logic that just doesn't handshake properly, and you have to fall back to something like Odin. So stand up a Windows VM if you need to, I guess. So obviously, in the description of this, you guys can tell why this is terrible, right? This is overly permissive. Most devices allow direct write access, except for like the few models I mentioned on US carriers. Newer protections exist for this, but they're very inconsistently applied and really don't even exist internationally, which is the majority of the phones that they make. So if you leave your phone at a Starbucks or something like that and you don't have user data encryption, you're pretty much boned. So be careful with that. We're going to talk a little bit about fast boot mode. This is more common. This is found on Nexus, HTC, Sony, Motorola, like any big OEMs like this provide that. This is also great for testing an image if you're doing, just straight up recovery building, because you don't actually have to write this to the flash. You can use fast boot, and it'll boot it off your machine and load it into memory. Saves you a flash cycle, saves you from overwriting a working file. And unfortunately, unlocking the bootloader to use fast boot most often, but not always, erases the user data partition. That is unless you're using something with published CVEs and problems, like Little Kernel. So Little Kernel is a Qualcomm bootloader. It's shipped on lots and lots of devices. And there's been some pretty serious problems with this. So I've called out these CVEs. You can research these. Most of these have been patched at this point on shipping devices, but Android, kind of, when a device comes out, a lot of times it's just abandoned. It doesn't get updates. So these things live for a very long time in the wild. So the first one, the fast boot just forgot to check the signature. Great job. So you could put whatever you want there and it just takes it. The second one's more interesting. It uses like the kubroot RSA attack to forge your own signature. So you can sort of apply a different signature check and build your own image and have it pass their verification. This is a very complicated one, so definitely follow up on that on your own and read out how that one works. And the newcomer here is the improper partition bounds checking when you're flashing a sparse image. So when you flash a system image, it doesn't really check where the sparse image ends, and so you can actually write past the boundary of where you're supposed to. This is pretty recent, and it's been patched already in their source, but again, these things live for a very long time. We mentioned download mode already. This is a good way to flash this, and I'm going to talk about laugh now. And of course, there's always things out there that are not covered in here. So laugh mode is a bootable partition named LAF found on many, many modern LG devices, including the Nexus 5, which is very interesting to me. It's a special boot mode similar to how you would get into download mode or recovery. You sort of do the death grip, as you call it, hold a certain button combination at boot time, and you get the phone to boot to something else. Communication with this is via a binary called send command. This is a Windows-only utility right now, but somebody has ported this to other platforms via Python now so that you can call this in whatever environment you live in. And this is essentially like a backdoor. It's like it drops you into a root shell if you send command the COM port that the device is plugged into. So here's an example of this happening on the Nexus 5. You boot into this mode, send one command, and now you have a root shell on this device. So this is very interesting that something like this is shipping, especially on like a modern Nexus device, but these are the reasons that building one of these images is important and provides you a way to like actually exploit a device and write to it like in this fashion. We're going to talk a little bit about a program called Frost, and this is sort of linking back to the forensics things that I mentioned you could probably use a recovery for. This stands for the forensic recovery of scrambled telephones, and a pair of German guys built a custom recovery, similar to like what we just talked about building, based on the Clockwork mod source, that provides the retrieval of encryption keys and things stored in RAM. And so this is kind of an interesting attack, and it's quite literally a cold boot attack. They discovered that if you freeze a phone after it's on and you've recovered it, and you put it to around 10 degrees Celsius, it slows the degradation of RAM content enough that it's possible to recover some of these things if you very quickly remove the battery and put it back in and get it to boot to your custom recovery. It uses a binary called AES keyfind to just snag AES keys out of RAM, so you can recover like a, your pin pattern passcode key via a method like this. So you can do this live from the recovery, or you can use Frost to do a memory dump of the RAM contents to your PC. Then you can search for these later. This requires sort of a contrived example, but it's an interesting way that it's possible to actually recover some of these pieces of information from RAM. And they actually executed this against the Galaxy Nexus, which is quite an old phone at this point. And it sort of requires the ability to quickly remove a battery. So on a lot of modern devices that you can't do that on, you're going to have to find some other way to short the power very quickly, which in a lot of cases means taking this thing apart. So not a super useful thing, but there are still lots of phones that ship with removable batteries, so it's something to think about there. So new protections. What are people doing about this? So now we have things on modern devices like init contexts. So things that happen in init scripts no longer just blindly happen as root. They're segmented to different user groups. So things execute, maybe you find some terrible permissions, but it's for a user that's useless to you. It doesn't actually help you in the exploit vector. So things like that are happening. Samsung and other OEMs have protections like Knox or Secure Boot coming out for more and more models. Unfortunately, Knox really doesn't matter on most devices because it'll just trip a flag, but that's it. It's a nag. It doesn't really actually prevent you from doing these things. With the release of Android Lollipop, Google provided a way, if you have a trusted execution environment like TrustZone or any manufacturer specific thing like that, to actually wrap the device key with the burned-in TrustZone key. So this prevents you from attacking off the device, because you have to now actually try and brute force on the device in order for this T to unwrap the device key. So in a lot of, previous to this, you could dump the contents of user data off the phone and just try and brute force a PIN or passcode, stuff like that. They've definitely turned SE Linux up to 11 on newer releases like Lollipop. And there's new system protections, like they just don't let you see into /dev anymore. So this hurts you a little bit in terms of figuring out how a device works, but it just slows you down. It doesn't actually really prevent anything. There's new concepts like DM Verity, and I say new because I haven't yet to see this in the wild, but they've provided this at least at KitKat. And this provides you a way to sort of like create a SHA-1 hash for each block of the system partition, and if any of those don't line up at boot time, it just won't boot. So things like keeping persistent root by writing to system are damaged in some sense by this because it'll see that you've modified it and just kill your ability to boot. Unfortunately, this is completely controlled by the kernel, so I've shown you many ways that you could just completely overwrite the kernel and turn that off if you'd like, so really not that great of a protection here. And of course, the sad face for force encrypt. This is something that supposedly shipped with Lollipop, and then Google did a 180 and decided, we're not going to do this anymore or force it in this version of Android. So the Nexus 6 and the Nexus 9 shipped with this. Nothing else running Lollipop really forces encryption, user data encryption anymore. So I would recommend at least that you encrypt user data if you care all about the data on your device. But I think we've shown enough examples of why this really isn't enough, because if you can control the kernel or other parts of the file system, you can kind of get around these things with something like an evil maid attack. So if you want to get started with this stuff, GitHub is definitely your friend. Somebody has probably already done the hard work for you. So if you have a device you want to investigate more, hit up GitHub. Device configs are all over the place. Again, many sites host stock firmware for Android devices. Like SAM firmware is a great one to pull down stock Samsung OEM builds. XDA developers, of course, there's lots of stock builds out there for different devices you have. You can pull those down there. You need to set up your build environment. I put a great guide out there on the CM Wiki that has like a step-by-step on how to get started with this. This is applicable to more than CyanogenMod, so this works with any source you want if you want to build whatever. The steps are largely the same, and it tells you sort of how to get all the packages you need for your build environment. Definitely review the links in the reference section. There's a lot of interesting CVEs out there. There's some tools I linked. And if you want to stay up on the latest that's happening in Android security, the DroidSec group is great. That's something I'm part of. There's an IRC channel on Freenode. There's a website. All the really interesting attacks kind of get talked about in here in real time. So if you find something or you're interested to follow up more, this is a great community if you're interested in that kind of stuff. So here's the references you guys can follow up on at your leisure. So I just wanted to thank CircleCityCon for having me and providing this platform to talk about these things. Here's all my contact information if you want to hit me up on Twitter. I have lots of device configs on my GitHub if you want to get started with like a common device here. Here's other ways to contact me. So thanks again, and just wanted to open up any questions you guys might have. Mm-hmm.
Is there any work being done in Android around the partitioning around some other layout? Is that a valid move? Is that madness? Is that a dark raffle and more slowdown? Or what?
It's a little bit of both. There's definitely work involved in that. It's very easy to completely destroy your device doing that, but it is possible, and a lot of people have done that, especially on older devices that give systems such little space, but then there's partitions that have tons of space that's unused. So people have tried to extend their system partitions to get a little bit more life out of their device. This is very dangerous, but it is definitely possible. And I think most people shy away from it because if you make a mistake, there's really no way to recover from that. So there's not really a lower level mode that can help you in a lot of cases fix that. On some devices, there's something called, on some Qualcomm devices, QPST is a way to communicate with the SOC at a very, very low level, but it's not a release tool, so it's something that's just in the internet and doesn't really have instructions or files to help you recover a lot of times. So yes, definitely people have done this, but it's pretty dangerous, so I would avoid that unless you don't care what happens to the phone or tablet. Anything else? Feel free to actually also afterwards to stop and if you have any questions, but thanks again, guys.